morning, everybody. Thank you all so much for coming out on this rainy Saturday morning. Welcome to Science on Saturday. I'm Dr. Joanna Albala. I'm the manager of the Science Education Program at Lawrence Livermore National Lab, and we're thrilled to have you here today. I'm so excited for this year's Science on Saturday theme, Up in the Air. The 4 talks this month will explore our innovative work with aerial and space-based equipment. We are very pleased this morning to welcome a special attendee. Astha Najem is the Constituent Services Manager for Congressman Swalwell, and thank you so much for joining us today. Can we give her a round of applause? Thank you. So, without further ado, let's welcome our presenters. Brian Weil is the Associate Program Leader for Autonomous Sensors. Brian received a BS in Computer Engineering and an MS in Electrical Engineering from California Polytech State University, San Luis Obispo. And there he is. Let's give him a round of applause. Joining him today is Claire Knight, a mechanical engineer and drone development and sensor integration specialist. Claire received a BS in mechanical engineering and an MS in engineering and technology management from the Colorado School of Mines. Joining them is Antonio Carrero Barreras, and he is an engineering associate. Antonio received an AS in Engineering Technology from San Joaquin Delta College and is currently working on a BS in Engineering Technology from Embry-Riddle Aeronautical University. Again, welcome. And joining our team from LL&L today is Roger Johnson. Roger Johnson is a high school teacher at Monte Vista High School who teaches physics and robotics and is also a faculty scholar in the Science Education Program. Let's welcome our presenters today. And now let's get started.
All right, so thank you guys very much for coming. So as mentioned, my name is Brian Weil. I am the Associate Program Leader for Autonomous Sensors at Lawrence Livermore National Lab. So we're going to talk a lot about that work today with the slides that you're going to see. You can actually see a picture on the top right of the team with drones flying behind them. So that's about the size of the team that works on a lot of what we're going to talk about today. But my background a little bit, so I've been at the lab for about 12 years now. Before that, I was born and raised in Fremont, California, so right over the hill. And went to Cal Poly to do engineering and was always involved in RC aircraft and unmanned systems, and then was very lucky as I got to the lab to almost create a career for myself with this program and do this type of work. So yep, very excited to talk to you guys today. I'll introduce Claire, or Claire will introduce yourself.
Thanks, Brian. Like you said, I'm Claire Knight, and as Joanna mentioned, I'm a mechanical engineer for the Autonomous Sensors program. I was born and raised in Santa Rosa, California, just a little bit north of here, and attended college in Colorado studying mechanical engineering and engineering and technology management. I joined the lab 5 years ago as an intern first, and then started full-time 3 years ago, and I had no idea that my path would lead me to work on drones, but I can say that's the best application of a mechanical engineering degree that you can do. It's been so fun, and during my time at Lawrence Livermore, I actually received my FAA pilot's license, as well as Brian and Antonio. We're all Part 107 drone pilots, so that's a really fun and exciting, unanticipated part of working in the Autonomous Sensors program.
Hi, and my name's Antonio Correa Barrios, and I'm an engineering technician at the Lawrence Livermore National Lab. I was born in Mexico City, raised in Manteca, just on the other side of the hill, and I've been at the lab for the past 12 years, and my journey there, my career, has exposed me to a lot of really cool and great science. I've got the opportunity to build tiny little targets that get blown up by giant lasers. I've also had the opportunity to make ultra-thin, like atom layer thick, metal films using vacuum technology. And now I get to build and test and fly drones with the Autonomous Sensors group. So thank you for coming to our talk. Oh, and my career there started with little more than just an associate's degree. So you guys out in the audience, you can get started in science and make a really good career without having to go directly to a PhD. So keep that in mind. And thank you for coming to our talk. So today we're going to explain to you guys or share with you what we mean by autonomous sensors, what that is. And we hope to share with you how sensors work and how we integrate them on autonomous systems in order to have them perform useful work. We're going to give you a little peek at how we make a system, such as a drone, like we use at Lawrence Livermore, and we're also going to explain some of the cool programs that Lawrence Livermore is supporting with this technology. But first, what is an autonomous sensor? And for that, I'm going to hand it over to my colleague Claire to give an explanation.
Thanks, Antonio. Yes, so let's unpack that. So Merriam-Webster describes autonomous as existing or capable of existing independently. So what does that really mean? It's the ability to have control over decision-making based on a variety of input factors, right? So you have the autonomy to decide, after you wake up, am I going to brush my teeth first or go eat breakfast first? Making simple decisions like that. Now, what is a sensor? The other part of autonomous sensor, Merriam-Webster defines that as a device that responds to a physical stimulus. So what is a physical stimulus? It can be any kind of input like heat, light, sound, pressure, and you can use sensors to pick up those things. Like my mic is picking up the sound of my voice, right? Your eyes are picking up the visible light that you can see around you. A thermometer senses change in temperature, things like that, right? So what is an autonomous sensor? We define that in our group as a sensor that responds to physical stimulus and then can make a decision about what to do about that physical stimulus. That's how those two parts of autonomous sensor work together as a system.
So now we have an idea of what we mean by autonomous sensors. And another word for autonomous sensor is robotics, which you guys might be familiar with, or intelligent systems, or uncrewed systems. And you might be familiar, they're in our everyday life. Just real quick, how many of you came in in a Tesla? All right, yeah, so you've been exposed to autonomous robotic technology already, right, with the self-driving, with the driving assistance and the autonomous driving capabilities. And if you've been out to San Francisco lately, you've probably seen the Waymos driving completely autonomous, almost completely autonomous, right? And then if you've been on an airplane lately, some portion of that flight has been performed with the use of autonomous technology. Think of guided navigation, autopilot. The airline industry is even developing and testing autonomous takeoff and landings, so be on the lookout for that. And you might be familiar with robotic arms in production facilities. So this technology can do hard and repetitive tasks day in and day out, around the clock, allowing manufacturers to produce goods at a reduced cost. And the technology is advancing to the point where humans are now starting to team and work together with this robotic technology. And one industry that might not come to mind right away when you think of autonomous technology is the agriculture industry. But in fact, farmers around the world are using this technology to grow their crops and produce goods at a reduced cost, much like the production facilities. Now, for example, a farmer could use a drone to automatically survey their field, find an area that needs nutrients more than others, and then deploy nutrients just in that specific area instead of spraying it on the whole crop. And this kind of technology is allowing them to farm at a cost-effective way. But not all technology is the same. So for a more in-depth explanation, I'm going to turn it over to Brian.
Thank you very much. Yep. Perfect. So we kind of talked about what autonomous sensors are, how we define them, and gave you some examples of different types of systems that you interact with in your everyday life today. But why? Why do we care? Why do we want to develop them? Why do we want to use them? And that brings in the concept of the 3 Ds of autonomy. That's what you'll see here. So the first D in the 3 Ds of autonomy is dangerous. So these are tasks, pretty self-explanatory, that are dangerous for humans to do, right? And the goal would be to get humans away from them, further increase what we call the standoff from that dangerous item. So we can use drones immediately, right, to basically go and look for things that might be dangerous for humans to be close to and interact with. We can even have them potentially interact with the dangerous item, and again, allowing the human to be much further away. Another type is dirty, and this can range from all different types of stuff. So this could literally be something that you're going to be in the dirt. So agriculture is a great example of this. Maybe you don't want to have to be in the field around dirt. Or potentially dirty and dangerous things, like spraying fields. So pesticides and stuff have been known to potentially have effects on humans. So we can use autonomous systems and sensors to, again, remove the humans from having to interact regularly with something that is considered dirty and potentially dangerous. And then the last one is dull. So these are like things that we don't want to do as humans, things that are just honestly annoying, right? Which autonomy is great at replacing. Driving is a great example, as Antonio mentioned. So driving the car is not exactly a fun thing. Maybe some of you guys will be getting your driver's license soon, and it seems fun, but after about 10 years, you'll probably realize it's not all it's cracked up to be. So this is a task that we can easily replace, and you're seeing that today. Another example would be something, and we'll talk about later, site security. So you'll see facilities in which they have security guards that walk around and check perimeters, right? And they have to do that constantly to make sure no one's trying to break an entry. That's something that today, in many ways, autonomous systems are already being used to basically do that patrol and not have to have a human constantly going around walking and looking for things. We can use cameras. We can automate that process very easily. So, as Antonio mentioned, not all autonomous systems look the same, and as you see technology develop, you'll notice that there's kind of a spectrum of what we generally call autonomous sensors and systems. And that starts with the left, with what we consider remote control, and that's really going to enhance humans. So that's kind of focusing, if we talk about those tasks again, the idea of dangerous tasks. The main focus is moving the human away, so we do something remote control. So we're getting them out of physical danger, we're increasing the physical distance from the task, but we're still requiring a lot of cognitive load. The human's going to be very much in the loop, paying attention. They're going to be focused still on the tasks they're trying to complete with the system. So it's helping, but it's maybe not the most value. As we move along the spectrum, we get to what we call semi-autonomous. And again, if we look at the car industry, this has been happening for a long time. When it first started, there were things like blind spot monitoring, right? Lights and auditory signals that would let you know if there was potentially a car in the lane next to you. They had lane keeping assist, which would tell you, again, through haptic feedback like vibrations or auditory or lights that you might be drifting into another lane, which would then tell you to correct back into a lane. Those are very helpful. They allow you to maybe not be as attentive to the driving process, but then would still engage with you to have you do the task to correct the vehicle. So again, very helpful, but maybe not as valuable as what we call trusted autonomy, where we're replacing humans, and then you get this idea of teaming. So that's really, again, if we look back at the car industry, that's where you are no longer driving. That's like in San Francisco getting in Waymo, hopping in the back, and the vehicle's going to drive. That is completely freeing up your time. You're no longer involved in the task physically or mentally. You're actually able to do a different task that might be involving what the vehicle's doing or moving on to something else. So you get in a vehicle, and you could take a meeting, you could have a phone call, you could read a book, right? You're no longer having to actually focus on the task at hand, and you completely trust that autonomous system to take over for you. So we'll talk a little bit about AI teaming.
Thanks, Brian. So here's an example of what AI and teaming looks like in an experiment that we did at Lawrence Livermore. So this is 5 different camera views of the same single experiment, and I'm going to break it down a little bit. So firstly, we have a ground vehicle. I may refer to it as a UGV, that's an uncrewed ground vehicle, and it is preceded by 3 aerial systems. So we'll call those uncrewed aerial systems, UAS, or drones. I'm referring to the same thing when I use those 3 terms. So here you can see the ground vehicle driving down a road, making a left-hand turn, and this whole time it's preceded by 3 UAS, 3 drones. So If you weren't using AI and teaming, this would require 4 operators, 1 operator for the ground vehicle and 1 operator for each UAS. In this instance, though, we have 1 operator who's remotely operating the ground vehicle. So that falls into the mode of operation that Brian outlined as a dangerous task. You would want the operator to have a standoff from the vehicle that is going and exploring this new space. And the way we're leveraging AI and teaming is that the 3 UAS actually have controls algorithms in place that tell them stay in this specific chevron formation, so that V formation, and precede the vehicle at a set distance. So you can see as it makes the left-hand turn, the aerial vehicles are swinging around to stay that set distance in front of that ground vehicle. Another fun thing about this ground vehicle, what's enabling an operator to have remote control of this vehicle is that we are mapping controls to the brake and the gas pedal, as well as the servo motor on the steering column, so that you have all the same functionality as an operator would that's in the vehicle, but you have this safety standoff. So the value added here is that what would take 4 highly skilled operators is now only requiring 1 operator who is at a safe distance standoff. So hopefully that highlights the value added of AI and teaming. All right.
Right. So now we've talked about what an autonomous system is. We've defined it, and we've talked about kind of the value of it, right? But now we'll shift onto the sensor side. So what are sensors, and how do they work? So the electromagnetic spectrum is basically a natural occurrence that all sensors operate in. And you guys are very familiar with this. If you look at the center of the spectrum up on the screen, you'll see the visible spectrum. That's what your guys' eyes use. So you guys are a sensor. You have ears that hear sound. You have eyes that pick up part of the electromagnetic spectrum in what we call the visible portion. And that's what you see as light going from red to violet. Now imagine that that extends further, because it does, into other areas that we denote with having lower or higher frequencies and lower or higher wavelengths. So what does that matter? Basically, we can make sensors that operate in these different areas. So if you look at the spectrum, you can see on the far left that we denote as having a much lower frequency is radio waves. And maybe not so much today, but it used to be that your TV signals would come over using radio waves. And if you get in the car and you're not listening to, say, Spotify or something over the internet, you can still tune into radio stations, local stations, and hear them. And that's all done with the radio portion of the spectrum. Now, if we move into higher frequencies, we get into microwaves. Now, they're actually called that because your microwave at home that you use to cook food actually uses these frequencies because water interacts very well with certain parts of that frequency spectrum. But this is also where you get things like Wi-Fi and cellular phones and radios that we use to communicate with. It's very common that they operate in the microwave band. Pushing even further to the higher frequency, we have infrared. Again, maybe not as prevalent as it used to be, but TV remotes back in the day used to have little infrared lights on them, and that's how you would communicate with them. Some still use it today. You'll also see some night vision cameras, like security cameras, will have these little LEDs that you don't see visually, but cameras will pick up. Those are typically in the infrared band, also known as IR. And then, of course, visible spectrum, we'll get to that in a second, and you guys are very familiar with it. But as you push up higher, we have ultraviolet, so that's where sunlight typically hits the Earth in. That's how the Earth gets a lot of energy from the sun. Your skin is a great detector of ultraviolet. If for any of you that have been out there too long without sunscreen, when you get a sunburn, that's how energy is typically absorbed with the skin. And then as we push even higher frequency, we get into things like X-rays. So any of you guys have been injured or had a medical procedure or have broken bone are probably familiar. This is what they use to do medical imaging typically. And then you push even to higher frequencies, which have very specific use cases in the gamma for nuclear type operations. But focusing on visible light to really hit home how we use the spectrum was something you guys use every day, again, is your sight. So your eyes are sensors that are very sensitive to this band denoted by wavelengths of 700 nanometers up to 400 nanometers. And again, that's how you perceive all the different colors of the rainbow, with red being a much lower frequency and violet being a higher frequency. And then your guys' eyes and your brain, through being able to process this data, can start differentiating and understanding how different objects relate to these signals. So in addition to using shape to identify something, say a table, you also may say, that's a black table, right? You know a color. And you can start doing this and using it to identify things. And that's exactly what sensors are going to do, and they do, is they use portions of these spectrum, and then they understand how they relate to certain objects we're looking for, and we develop the algorithms to then do the detection on top of that. And then we're going to talk a little bit more in depth as we show you a demo. So if I can bring Roger up for this demo. We're actually going to show you, yes, a round of applause.
Thank you. Okay.
So it should be good. So this is an infrared camera. It actually does two things. It has infrared, so again, it's going to be in that IR band that I talked about earlier, just below visible spectrum. And it also has a camera in it that's going to pick up visible spectrum, the same thing your guys' eyes pick up.
Oh, yeah,
There we go.
Maybe. Okay.
Well, okay, so you guys can see. Yep, wave to the camera. So this is, again, this is an infrared camera.
Nice.
Mic's on.
Yay.
All right. So basically, the infrared band is really good at detecting temperature. And you can see different materials. So you can see how we can basically see body temperature from this, right? And then we can see that face, probably hotter, clothes are absorbing your body heat and re-emitting it. Now, so bodies, clothes, things like that are really good in the IR band. We can detect the heat coming off of them. However, there are materials that are much harder to see because they reflect. So you can see that this emergency blanket is actually really good at reflecting in the IR band. So we're no longer detecting heat. In fact, we're detecting what's reflected from heat. So if I move around, you might see different parts of the room getting reflected to it. So it's almost like a mirror when it comes to infrared. However, you can see it pretty well in the visible spectrum. You see the structure of it very well. But if we were to move to a different material, say something like a plexiglass, which you'll see Roger carrying now, this is very interesting because it is actually very reflective, this upstates, to the IR. So not only does it have the same properties of reflecting like the emergency blanket does, it's also relatively clear. So if you wanted to detect, say, plexiglass, you would not want to use the IR or the visible band because it's almost invisible to both of those. Whereas humans are picked up on both. The reflective blanket does not show IR, but shows camera. So that's kind of showing you that different sensors have different abilities to see all different types of materials, right? And we're going to use all different ones to start detecting different things. All right.
Oh.
So,
Yeah.
Antonio, I'll take it away.
That was pretty fun, right? How about a round of applause? All right, so a lot of you future scientists and engineers might be wondering, first of all, that's pretty cool, right? And how do we build a system? Well, there are four major components of an autonomous sensor. The first part is the sensor, as we've just seen, acts as the eyes and the ears of the system. Then there's the platform. So you can think of this as the skeleton and the muscles of the system. So if you look at the picture, if you look at the frame of the drone, that's like the skeleton where all the components get attached to. And then the motors act as the muscle that help the drone push and pull itself through the air. Another major component of autonomous sensors are the algorithm and the processing. So as the sensors pull in all this information, it's got to go somewhere. So it usually goes to a processing unit that takes that sensor information, runs it through algorithms, which are a specific set of instructions, and then from that, it calculates what to do next with that, from that information. And that's how we get autonomy. And in this area, that's where AI, artificial intelligence, lives, per se. Then another major component is networks. So this is how drones communicate with each other and to a central point. So think about a bee, a single bee in a large swarm, how that one bee can take information, think, and process, and decide what to do next based off what its neighbors are doing. And that's how they keep from running into each other. And now we're going to give you a sneak peek at how we at the lab build these autonomous sensors.
Great. So here's a video that shows a little bit of what our day may look like. So here I'm working with another mechanical engineer in our program area where we designed the UAS, the drone platform, for a specific sensor application. So first we use computer-aided design software, CAD, as you saw in the first little clip. And after that, we decide how we're going to manufacture it. So are we going to use traditional manufacturing techniques? Are we going to 3D print? And generally, it's a combination of a variety of different manufacturing techniques that go into creating one platform. So here, I'm using a 3D printer to print some of the components. And now it might not look like the 3D printers that you're imagining, because it's not a fused deposition modeling type of 3D printer. Those are the ones that extrude material. You can imagine like how a hot glue gun works, right? It's squeezing out the material and creating layers and layers to build up a part. That 3D printing technique is called selective laser sintering. So there are just a variety of manufacturing techniques that we use. Then we also move into the assembly and integration of parts, and Antonio can highlight some of that.
Yeah, so the assembly, so there's a lot of components to these drones, and it takes a diverse set of people with a diverse set of skills, such as, along with what Claire was saying, mechanical engineering. There's also electrical engineering, computer science, data science, and networking. And then all those skills come together to contribute their components to build a larger system. Now, as you see here, once all these components come together, we gotta find a way to make sure that all these components kind of mesh and work together seamlessly. So you gotta test them. So we are capable of field testing our entire systems. As you see here, is an example of our outdoor testing lab, where we can take the systems that we built and fly them in a real-world environment and collect data as well. Okay, the video ended, but you saw there how it was going down that lane. So at the same time it's going down the lane, it's collecting information that then gets sent to the machine learning portion of the system. And Brian's going to talk more on that.
Yeah, so now you know what they are, you know how we build them, but again, what do we use them for? What does Lawrence Livermore do with these autonomous sensors and systems? So now we're going to talk about a couple different mission areas that we're currently working on and also getting more involved in. So the first one we're going to talk about is explosive hazard detection. So the systems you see here on the screen are using ground penetrating radar, or GPR, and they're emitting electromagnetic spectrum into the ground. In fact, these sensors specifically are in the microwave portion. So they're emitting microwave signals into the ground that will basically go and penetrate the subsurface and then reflect back. And we use that information that we collect to tell us what's going on under the ground. And you'll see specifically in the next slide how we do that. But these systems are designed to be very flexible, and they are basically able to go on a small unmanned aerial system or drone that you see in the bottom picture, or on larger vehicles like off-roading ones, which you see in the top. So what do we do with that data? Oh, sorry. Get the video playing. So we process this data in real time. Again, the microwaves that we transmit to the ground and receive back across what you saw on the front and the bottom of the vehicles to create 3D images of the subsurface. So traditionally, ground penetrating radar, you would get that top grayscale image, that black and white image, as an operator. You would be given what we call this raw data to then try to understand what's going on in the subsurface. Okay. So when we talk about autonomy, we don't just mean with the platforms and the vehicles themselves, we also mean it from how we use the data. So instead of having to have a trained expert that would need to understand what those black and white images mean as far as what's going on in underground, we take that a further step and we process it to create very intuitive things that people can look at and understand what's going on. So that it doesn't take an expert, it doesn't take 20 years of experience, it doesn't take a very technical person to use it. Someone can hop in these vehicles or see a screen, again, if we're increasing standoff, and understand what's going on in the subsurface and ultimately avoid any hazards. So what we provide, you saw in the video scrolling up top, but also in that bottom picture, in that middle strip, that's in an RGB image, a red, green, blue image, you can actually see concentrated red blobs where there are objects. So it's, again, much more intuitive for someone to understand what's going on. And then we take it a step further. We don't just provide the imagery, but we use advanced algorithms and machine learning techniques to do auto detection. So again, if you remember when I was talking about that spectrum of value, we go from a very well-trained operator that would have to be using a lot of mental focus on understanding data coming at them, to an imagery that would definitely, you could kind of keep a view on it, you'd understand what's going on, all the way to fully automated detection in which this system could alert you if it sees a hazard that you should avoid, right? So this is getting to that trusted autonomy where you are no longer having to be a man in the loop, really paying attention, and you can just be alerted when there's an issue going by.
You can keep it, yeah. I'll talk about the next mission area, which is airfield or runway damage inspection. So you can imagine whether there is intentional damage done to a runway or just degradation due to weather or other environmental factors. You want to ensure that you have a safe place for aircraft takeoff and landing, right? And so one way to observe damage is in the visible spectrum, right? You can see it with your eyes, you can see it with cameras. In this example, you can see that there's a crater underneath this drone, so that's a pretty obvious indication that you would want to avoid that space in a runway or send someone to repair it for a safe takeoff and landing. But what about those instances where you can't see damage? Maybe the subsurface under the runway, the rebar is damaged, or there are some voids, some air pockets, and things like that. Something you can't see with the naked eye, but wouldn't support an aircraft takeoff or landing. You have to use a variety of other sensors to detect things like this. So one of those sensors could be a ground-penetrating radar, like Brian just mentioned. That's a great application to see subsurface disturbance. After you use a variety of sensors to detect what could be damage or areas that you want to avoid, you can combine different sensor data into something like a heat map that would be using autonomy to inform a user of safe or dangerous spaces in a runway. And one way to do that is create a heat map, like you can see on the screen, showing very obviously not taking a lot of decision making for a human to say, I'm going to avoid those red areas. Those were either visibly noted as being dangerous or destroyed, or not visibly, whether it was with radar or something else. And then those green areas are safe for aircraft takeoff and landing. So it can create a picture combining all of these different sensors to inform the user, requiring very little brain power for the operator. And again, you can use a variety of sensors, like the radar falls in the microwaves. You can use infrared falling in that next section of the electromagnetic spectrum, as well as visible light in normal cameras. So that just highlights what sensor range you can use to apply to a mission space like that.
Right, so another area that we're going to talk about, I mentioned a little bit earlier, but the mission area of site security. So again, these are cases where you have an area you want to protect. You may have a fence line. Again, you can think of maybe some facilities that you see where you have security guards walking around it. We typically focus on much larger sites that the government typically uses where security is a must. So what do we use to do this? Here you see one portion which is in the optical area, again using visible cameras, although we can also use infrared cameras, again like you saw demonstrated, and then also things like LiDARs, which we'll talk a little bit about later, which give you the idea of 3D structure above the surface. But in here, using visible cameras, you can see that we've developed automated detectors using relatively low-cost drones and hardware to basically fly and cover area very quickly and then identify objects that might be related to concerning activities. Here we see the algorithms automatically detecting a truck and a generator, which might indicate maybe some type of construction activity, something that you wouldn't want to see going near, say, a fence line of a site you want to protect. But we go a step further again, because detecting, say, a generator and truck is very valuable. It's not requiring someone to walk around and constantly look for these things. It can, again, alert if it sees these objects. But then we can also group together what objects it's seeing in one scene and get an idea of what type of activity is going on. So I just mentioned you may look at this and, again, see a work truck and a generator and say construction activity. we can have algorithms that automatically do that. And again, instead of just alerting certain objects, we can actually alert you of specific activities we think that are going on. And again, that just adds more value, right, to the system. Other sensors that we use in this area are spectrum detectors. So what you see here might be a little hard to see, but this is a plot showing across a broad spectrum. This is actually covering roughly the microwave and a little bit lower that we talked about earlier, to show you what type of transmitters are going on in the area. And these peaks are showing you where there's a lot of energy, meaning you're expecting a lot of activity going on. And these can cover things like cell phones, handheld radios, Wi-Fi. And again, what we can do with this is get an idea of different activities going on where people are communicating. And if it's an area where we wouldn't expect a lot of type of communication going on or a certain type that we would associate with an activity, we can then again alert people, say, hey, this is somewhere to pay attention. So with a single spectrum analyzer, you will see that kind of plot with all the green and blue on it, and then identify what's going on. But then if you took multiple of them and moved them around, say with an autonomous platform that we showed you earlier, you can actually generate a heat map, and that's what you see in the lower left, which is showing you a geophysical map, so like something like Google Maps, of what type of communications are going on in a certain area. And again, that just adds more value to understanding what type of radios, cell phones, things are going on in an area and relate them to certain activities. And again, this basically is focusing on the FM radio, TV radio area, but also a little bit into the microwave. So we are actually going to demonstrate to you guys what a spectrum analyzer does and what you can use it for. So I'm going to bring out Roger again. Okay, so just as you saw on the picture we had, this is a spectrum analyzer. So from left to right, you're seeing the live spectrum of what's going on in this facility. This is covering roughly 11 megahertz to 6 gigahertz. So again, as I talk about the electromagnetic spectrum, that's covering radio all the way up to microwave area. So you can actually see right now, there's a lot of you guys in here. Some of you probably didn't turn your cell phones off. And we can see that. All that little noise on the left-hand side is typically associated with cell phone traffic. Wi-Fi will be in the higher area to the right, where we get into 5 gigahertz and 2.4 gigahertz. Roger has a handheld radio that's at a low frequency, so when he chirps it, you're actually going to see it says overload, and you see a big band. Go ahead and let go, and then go back up. See that big peak that's showing?
Yeah.
That's detecting the radio. So again, if you were looking for handheld radio traffic, people doing maybe long-range comms that they don't want you to detect because this is not over a cell phone, so it's a little harder to see, you could see the radio traffic with the spectrum analyzer. Now, the other thing you can do, again, is something like Wi-Fi. So on the, move my cursor, on this side of here, so you see one peak, that's probably related to Wi-Fi. Again, there's a lot of devices going on. But if I take my cell phone, which is connected to the Wi-Fi, and I actually start some traffic going across it, you'll see in time that a much bigger peak is starting to show up between those two on the right side, kind of near where my cursor is. So that's my cell phone traffic going. So again, we can use devices like spectrum analyzers to not only see if there is different if there are communications going on, but also different types.
All right, I'm going to discuss another mission space, thank you, in an area that is more tied to environmental research and keeping our planet green. So this mission space is centered around orphaned natural gas wells. So that means natural gas wells that have been abandoned, forgotten about, are no longer used, but still may be leaking methane gas into the atmosphere. So you can imagine the need that if these are leaking hundreds of grams, kilograms of methane into the atmosphere, that we would want to go and cap them so that they're no longer leaking, right? The undocumented portion of this is interesting because decades ago, people who are placing natural gas wells may not have noted exactly where they are, or those documents may have been lost. So to find these natural gas wells, you need to use a variety of sensors. The alternative would be that humans just go and walk across large expanses of the country in search of these, and that would fall pretty heavily into the dull category of why we would want to use autonomy. So you can multiply your force by using autonomy and using different kind of vehicles equipped with different sensors to pinpoint specific areas that you want to deeply investigate. And an important detail that I didn't note at the beginning is that there are hundreds of thousands of these estimated across the United States. So you can imagine the millions of hours that it would take humans to find these. So that's why autonomy plays a really big part in the detection and location of orphaned natural gas wells. So what characteristics can you use to locate these natural gas wells? As you can see, I'll just go back for a second, they can look very different. They can still have an oil derrick on them. They could just be a pipe sticking out of the ground. So they really vary quite widely. So one way that you can detect these is using a magnetometer. Now, magnetometers detect changes in magnetic field. So with a pipe going deep into the ground, when you use a magnetometer, it'll detect a very strong change in magnetic field due to the ferrous material being drilled really deeply into the ground. Now, using magnetometer data isn't really of value unless you can visualize it using algorithms to create a heat map like you can see here on the screen. So those big changes in magnetic field are denoted by these bright spots, the yellowish green, and then the background where there is no notable change in magnetic field is still color mapped in blue. So you can focus specifically on going to investigate these bright spots and then use other sensors to characterize what is actually happening at those bright spots. I will make a quick caveat that a magnetometer does not fall specifically in the electromagnetic spectrum. Magnetism is a property of the electromagnetic waves, but it is still really valuable in terms of a sensor that can be combined with other sensor data in the electromagnetic spectrum. Now, other sensors that may be used to really inform the user of what kinds of things you are detecting are LiDAR sensors. So these fall in a range in the electromagnetic spectrum. And the way you can use them is by essentially topo mapping the surface using topography. So it's showing change in elevation. So you can imagine like the big oil derrick sitting on top of an orphaned well would show up differently than just a pipe sticking out of the ground. And finally, once you narrow down to noticing these specific locations that you want to investigate further, you can use methane gas detection sensors that are using different wavelengths to identify if methane gas is being leaked into the atmosphere. So you can use a combination of a variety of different sensors to give you a very informed decision as to whether or not you've A, found an orphaned natural gas well, B, if it's leaking into the atmosphere, and C, it can give you details as to how to cap it and how to prevent it from continuing to leak.
So the last mission area we're going to talk about is wildfires. So this is perhaps good timing because if you guys are seeing in the news what's happening down in Southern California, there's a lot of issues and devastation going on with wildfires. So this is something that obviously plagues our state very heavily in the last decade, but also we're seeing it across the world. If you guys remember a few years ago with Australia, they dealt with some very large bushfires, and that's something that's becoming part of their reality as well. So obviously it's a huge problem, and one that's ripe for autonomous sensors to be applied to. So if you guys are local to the area, you may remember, I think late this last summer, we actually had a fire that started between Livermore and Tracy in the hills where actually part of Livermore Site 300 is. And it burned quite a bit of acreage, including some of our facility area. And this team was actually called upon to take some of our sensing technology out there and see if we could help with some of the post-fire response. One of the main things being looking for what we call hotspots. So hotspots with fires are areas where the fire has previously been burned and put out, or areas that didn't burn that we didn't think burnt, but might still have a very hot spot that could cause fires later on. And why these are such a threat are they are very, very difficult to see, but pose a huge threat in that when there's high winds, which typically there are during a fire, they can blow embers, which can cause fires for miles away and restart fires. So what you actually see on the screen here is us flying some of our thermal technology. So again, like the IR camera that we showed you, and using cameras to detect these hotspots. And you can see very clearly that they pop up. So just as you guys saw your faces in the crowd, the fires pop up very well as well. Now, if we go to the next slide, you'll see when we went up for visual confirmation on the left, it's very difficult to see these with the human eye or just with a simple camera. Then in this case, it was under the ground, and it really wasn't exposed too much until the wind blew. And by that time, again, it's kicking off a bunch of embers, which could cause huge problems. Basically, the damage is already done. So this case, you saw in the previous image that the thermal camera picked that up very, very brightly, and we're actually able to communicate with local fire department to put that out because, again, it's considered a very serious threat for restarting fires. So this is an area that obviously, again, is huge for California, it's huge for the nation, and even broader, and it's something that we're getting more and more involved in. So now we are going to do a drone demo. I believe Antonio can hear us. Antonio snuck away. And he's going to be flying a drone, and we should be seeing the live feed come on the screen. So we'll give that a second.
All right. So due to the weather, unfortunately, we're not going to be flying around campus.
There's our pilot.
Oh, yeah, there you go. Nice! All right. So he'll just be flying in the atrium. So there's a camera view on this drone. Great, as you can see, he takes off. A couple different things going on.
We're all excited to see.
I know, I'm invested myself as a viewer. So in addition to all the sensor integration and all of the applications that Brian and I have been talking about, we do design and develop the platforms for these sensors in-house at the lab. And so that's what we're highlighting here. This is just a little tiny drone compared to the ones you've seen in the pictures of some of our other work. But there's a lot that goes into designing and manufacturing drone platforms. It seems really straightforward because now you can buy small drones off the shelf and they just work right away. But that's not typically the case, especially for our larger platforms. You have to do a lot of electrical integration and a lot of specific tuning for the platforms, depending on what payloads, what sensors you're carrying, and things like that. Awesome! There's a round of applause in here. Great. Is there anything you'd like to add?
Nope,
Okay.
good. So yeah, so just to recap what we learned today, so again, we walked you through what an autonomous sensor is and defined that both formally and then also typically what type of autonomous sensors and systems you see out in the wild today. We told you a little bit about how sensors work and how you can detect them in the electromagnetic spectrum. And then we showed you how you build them. So what type of careers, what type of people, and what do the teams look like when you're going to be building and developing these things. And then finally, we showed you specifically what Lawrence Livermore is doing with this technology to try to meet the demanding needs that our nation faces right now. So we'd like to bring Roger back on. I think he might be, oh, there we go.
So if you are thinking, that looks like a great career or really cool thing to do, and wondering how to get from where you are now in school to there and into their jobs, you want to make sure that you're taking some math classes, if there's a physics class available to you, but also look at getting involved in other activities. So if your school has a robotics program, whether it's FIRST or VEX or other kinds, or if there's engineering classes, programming clubs, all of these things will help move you along so that you can find yourself flying drones for a profession too.
So yeah, thank you guys.